Swayam Prabha. Digital India. Educated India.
Now in this lecture, we will focus primarily on the moment frame resisting systems, and there are two distinct types of moment frame resisting systems. One is known as ordinary moment resisting frame. The other one is known as special moment resisting frame. There is also another variety which is prevalent in American courts, which is known as intermediate moment resisting frames, but that is not mentioned in the Indian courts, so I will not talk about that here. So how does a moment resisting frame typically works? If we have this frame and we have these two forces P1 and P2 acting on this frame would want to deflect laterally. In the process, it will develop a bending moment diagram like this. And any of you who have taken basic structural analysis would know that this is how the bending moment diagram could be. There will be points of inflection in each member here. And so basically, essentially, each member would be under a double curvature kind of a scenario. Now, since we are interested primarily in connections, so if we look at the connections here, these connections will be subjected to bending moments in this manner. There will be bending moments coming from the columns, which are both, for example, if this member is shifting right ways towards right, both these moments will be in the clockwise direction. And the moments that are coming from the beams, in this case there is only one beam, there could also be another beam, and if there are two beams, both moments will be in the anti-clockwise directions and they will balance each other. In addition to that, there will be large shear force demands on this one. So there will be shear forces coming from the connection, from the columns, and there will be shear forces coming from the, which is marked as VB here, shear forces coming from the beam. And all these forces, along with the axial forces, if there are any, they will be in equilibrium, and they will be introducing different types of bending moment shear force demands on the connection. The connection needs to be designed for these forces. So as I was talking about an ordinary moment resisting frame versus a special moment resisting frame. So an ordinary moment resisting frame is basically a less ductile type of a rigid connection. It's also a rigid connection. Sometimes even semi-rigid connections are also permitted or can also be considered as an ordinary moment resisting frame member or element. But special moment resisting frames have to be rigid connections only. The requirement for ordinary moment resisting frame is that it should be able to, a connection that is a part of ordinary moment resisting frame, the connection or the joint should have the capacity to at least resist or to at least accommodate a 0.02 radian rotation without any loss in strength. What do we mean by this much of rotation? Basically, if we can think of a column like this and a beam which is connected to this column rigidly like so, and if we, let's say, have these columns in fixed position and the columns are very rigid, they don't move, and the beam moves, the beam should be able to move by an angle which is 0.02 radians. So this column would be undergoing a kind of a elastic deformation or plastic deformation of 2%, which is basically 2% of the story depth. So 2% of the story height. So that is the level of plastic deformation or overall deformation it should be able to accommodate. There is for a special moment frame, however, this requirement is more stringent and it requires at least a 4% or 0.04 radians of relative rotation between the beam and the column without any loss in strength. So that's a very critical aspect. Now, how do we know which connection is eligible or which connection is capable of undergoing this kind of a deformation without any loss in strength? For that, we can use, we can go to IS 800. There is an annexure F, which is taken from Bjorhove's research, wherein they have developed some nice connection, these curves which relate the rotation with moment, and then there is a limit that is set according to this equation. So for various types of connections, these equations have been developed, and we can actually fit our connections. Depending on all the parameters that the connection has, we can actually find the values, and then we can find out what is the rotation capacity of my connection, and that should at least satisfy the 2% or 2 radians or 0.02 radians or 0.04 radians requirement. Also, for such connections, IS 800 specifies that only E250B grade of steel can be used in the entire frame. So in a special moment frame, since we require a larger level of ductility, and also since we want these frame members to behave as if they are to behave as a ductility or deformation controlled member, we don't want them to have very high overstrength. So therefore, it is required that these members should not be of a greater grade than E250. However, in the revised code, now there is an allowance to use even higher grade steel, that is even 350 and so on can be used, but they should still be having a certain amount of high toughness. So high toughness requirement is not relaxed, but the strength can be higher, and accordingly the other neighboring members can be designed. Ordinary moment resisting frames, both the ordinary moment resisting frame and the special moment resisting frame have certain restrictions. One is that only high strength friction grip bolts can be used in both of them, because they are subjected to cyclic loading conditions. And when we were discussing the bolted connections, we did mention that whenever there is a possibility of a cyclic loading, only high strength friction grip bolts should be used. That is mentioned in IS 800. Also, the same code mentions that in the locations where there is supposed to be a butt weld subjected to critical loading conditions, only complete joint penetration weld should be provided. That too, the weld electrode should be of high toughness, and the welding procedure that is followed should also lead to a high toughness welding. In certain cases where the groove welding is provided in a column splice, it may not be required to go for a CJP, complete joint penetration type of weld, especially when in the situations where the column is primarily going to remain in compression. As we have discussed before, the ordinary moment frame offers less level of ductility in comparison to the special moment frame, and therefore the requirements in special moment frame are more stringent. For example, ordinary moment frames can be used only in for resisting earthquake loads only in earthquake zone 2. So that is the zone which has the least earthquake risk in India. And IS 800 mentions that OMFs can be used in zone 3 buildings also, as long as the buildings have an importance factor of less than or equal to 1. That is not very critical buildings. For all other buildings, that is in zone 3, all the buildings of importance factor greater than 1, or in zone 4 and 5, we should always only use the SLF. IS 1893 part 1 again differs slightly with IS 800. The IS 1893 says that OMFs can be used only in zone 2. So they don't allow, the IS 1893 does not allow the use of OMF in zone 3, even for less important buildings. Also, there is an important philosophy which, when it comes to the design of earthquake resistant structures, which is known as strong column weak beam design philosophy. So this approach is not mandatory for ordinary moment frames. However, it is mandatory for special moment frames. What do we understand by strong column weak beam theory? So at a joint, the idea is that under the earthquake loading, the hinges would form, but those hinges should not form in the column. So like for example, in this frame, at this location, if the hinge has formed in the column, that leads to a complete instability of the structure, and then the structure could collapse. However, if these hinges don't form in the column but they form in the beam, then that allows a much more ductile and much more stable behavior, and allows for a progressive kind of a yielding of the structure. So in order for this to happen, we have to look at this joint. Let's say this is that center of the joint, and we have beams going in this direction and columns going in this direction. So the combined moment, which is, for example, in this case, the combined moment of the columns is going in the clockwise direction, and combined moment from the beams is going in anti-clockwise direction. The combination of moments in the beam, the moment capacity of the beam, the two beams combined, should be less than the moment capacity of the column, so that since the two are going to balance each other, if the beam has a lower capacity, it would fail first, and then we have to make sure that it has ductile detailing, so that even though it yields first, it does not necessarily leads to a drop in moment demand from here, but it allows for larger deflection in the frame, and in return it will absorb some seismic energy. So IS 800, for example, gives this provision wherein you are required to calculate the moment capacity of the column at a joint and moment capacities of the beams at the same joint. You add them up, and then the ratio of the two should be greater than or equal to 1.2. This is very similar to other international standards that are prevalent. Now there could be some variations in the way this MPB or MPC are calculated. Sometimes they are calculated including the slenderness effect, sometimes they are not. The new draft version of the ductile detailing, for the ductile detailing of steel structures, gives a very stringent requirement. So this also has the same philosophy, wherein sigma MPC divided by sigma MBO should be greater than or equal to 1.8. So this says that the column capacity at a joint should be at least 80% greater than the beam capacity. This, in my opinion, is very stringent. We are still yet to get more details on this code. I hope as the time progresses, we will get more details about this code. So essentially what they are doing here is that they are giving more details on how to calculate this sigma MPC and sigma MBO value. So for the calculation of bending moment capacity of the beams, they are adding a factor of 1.1, which is just kind of a reserved strength, which they are accounting for just in case there is an additional strength. Ry corresponds to the difference between the characteristic strength of the material and the expected strength of the material. So a 250 yield strength steel would have a characteristic strength of 250 MPa, but an expected strength could be, yield strength could be higher than that. So whatever that value is, the ratio of the two should be used here, and then that is the plastic moment capacity and the yield stress. So that would give you the moment capacity of all the beams that are connecting to that joint. Similarly, another formula is available for calculation of the capacity of the columns. So here you may see that this factor of Ry and 1.1 are not used because we want to be conservative. And in addition to that, the slenderness effect is also included, because if the slenderness reduces the capacity of the column, that effect is included by this factor. Okay? So if you have learned how to design slender columns, you would have come across this this expression, which actually accounts for the reduction in strength in a column because of the slenderness effect. Now, the only issue, in my opinion, is that 1.8 factor seems too large. Maybe there is some rationale for that. We have to hear more from the committee to understand it fully. So, as we have just seen, that the code requires, the existing code IS 800 requires that the columns should be stronger by more than 20% than the beams. So columns moment capacity should be at least 20% greater than the beams moment capacity, and that is true even for ordinary moment frame and special moment frame if they are using rigid connections. However, ordinary moment frame allows the use of semi-rigid connections, and when it allows for the use of semi-rigid connections, then the connection should be stronger than 0.5 times the plastic moment capacity of the beam. Whereas in the case of special moment frame, the connection should be always be rigid, and it should be at least 1.2 times the plastic moment capacity of the beam. Now, what is the strength of the connection? The strength of the connection is basically corresponding to the strength of the weld and the way the force is transferred from the beam to the column. There is also a provision of using a reduced beam section, and a schematic of such a beam system is shown here. Here you may see that the beam cross section is uniform almost up to the point where it is connected to the column, but just before that it is reduced artificially in a very smooth manner. And the idea here is that we want to artificially create an area which can be designated as the hinge area, and when a high moment demand comes, it does not produce a failure here, but it should produce a large amount of yielding in this region, so that the failure can be prevented. Failure at the connection can be prevented, because the fear is that a connection failure, which would probably be a weld failure here will be catastrophic, whereas if we can move it away from the column, it will be more gradual and more manageable, because it will be yielding driven. So in such a section, if such a cross section is used, the connection, it is prescribed that the connection should be stronger than 80% of the plastic moment capacity of the unreduced section. So the taking both of these provisions simultaneously, what it means is that this connection should be 20% or 1.2 times stronger than the reduced cross section's moment capacity. At the same time, it should also be at least 80% or stronger than the, should be stronger than at least 80% of the moment capacity of the section away from the reduced section, so unreduced section. In order for us to know the rotation capacity of a connection, presently we have to go to annexure F of our IS 800, which gives a very cumbersome process, and it would be very, very difficult for a design engineer to actually be able to calculate the rotation capacity of any given connection design. What American standard AIC 358 does is that it prescribes, or it provides a list of some pre-qualified special moment resisting frame connections. So some of them are shown here. Some of the diagrams are shown here. So these connections, the diagrams are not giving the entire information. You have to go to this code and find out the different dimensional requirements for these connections. And if you fulfill those dimensional requirements, then you can be assured that this connection will be able to develop, or you will be able to use it in the special moment resisting frame, meaning that it has adequate rotational capacity. So for example, if the rotation capacity should be at least 4% or 0.04 radian, then these connections, as long as you follow the guidelines of these connections, you would be assured of that much of the rotation capacity. In Indian code right now, we don't have any such provisions, and that makes the life of an engineer a bit difficult. I think IS 800 should also develop some such pre-qualified connections which could be handily used. Another aspect of a ductile design of a beam column joint is the development of a panel zone. So a panel zone is basically the intersection between the beam and the column. So when we have, let's say we have a column, and then we have two beams coming and meeting this column at this region, and then these beams wish to or want to rotate in this fashion, and let's say the column is held in its position. So this will basically produce some kind of a shear zone, shear panel zone in this system. And that shear panel zone, this will be a shear panel developing in the column web, which is generally considered to be very ductile in nature because it is governed by shear yielding of the column web. However, if the column cross-section plasticizes significantly, that can lead to an overall instability. So there are a couple of requirements in order corresponding to the performance of such shear panels. So for ordinary moment resisting frames, the shear panel are not required to be particularly designed, and only the continuity plates are required in rigid connections if end plate connections are not used. If end plate connections are used, then we can assess the requirement of continuity plates. They are not mandatory. If we are welding the flange directly to the column, flange of the beam directly to the column, then it is continuity plates are mandatory in ordinary moment resisting frames. In the special moment resisting frames, however, we have to check the behavior of the panel zone. Even though it can deform in a very ductile manner, excessive deformation here can lead to instability of the column itself. Therefore, we should make sure that the panel zone, even though it may plasticize to some extent, it should not undergo shear buckling. So those requirements have to be satisfied. And continuity plates are always required except in the end plate connections. So a panel zone, when we are designing it, we have to calculate the shear force demand on the panel zone, and then we have to design it for that kind of a shear force. So because we want to avoid large panel zone deflections, for two reasons. One, a very large deflection in the panel zone will make the column non-straight and create instability in the column. That would be very risky for the structure. Plus, also because of the large deformations right at the tip of the weld here, we can expect cracking to start. And in order to avoid that, we should avoid excessive rotation of the panel. How do we calculate the shear force demand in the panel? So the guideline could be straightforward. Basically, we know the moment capacity of each beam on each side of the panel, and we are assuming that this beam is going to yield or plasticize under high bending moment demands. So therefore, we know the moment capacity of each of these beams, M1 and M2. What we do is we take this moment capacity and we divide it with the lever arm, so that we can get the tension force demand and the compression force demand in the flanges of the beam. So those tension and compression force demands on the flanges of the beam are calculated. Then those two flanges, since both beams would be rotating in the same direction, those flanges would be applying a force on the panel zone in the same direction. So we add these two forces, force coming from the top flange on one beam and force coming from the top flange of the other beam, and then we add them together. In addition to that, from our structural analysis, we would have calculated some shear force demand in the column top. So that shear force demand we deduct, because that is the only force that is balancing, or that is kind of acting against these two forces, and that will give us the net force acting at the top edge of the panel. The same force must be acting at the bottom edge of the panel in order to resist it. So basically that gives us the shear force demand, and then we need to take the cross-section area and design for that shear force demand. This is the expression that I've just explained to you to calculate the shear force demand in the column panel. In addition to these, there are also a couple of other requirements. One such requirement is the use of plastic type of slender cross sections. So you might recall that whenever we wanted to avoid local buckling of a cross section, we were required to use a semi-compact or compact cross section based on different provisions. We were never using, until we talked about earthquake engineering, we never used plastic cross sections. We never discussed this column. So this column is relevant when it comes to earthquake performance of a connection. So when we are designing a member for which is a part of earthquake resisting frame, if it is near a region where we are not expecting any hinge to form, so for example, all the FCEs, they can be designed to have a compact classification. They don't have to be very stringent. Compact cross sections are sufficient. However, in the regions where we are expecting the cross section to undergo plastic deformations, which is basically the DCEs elements, there we cannot have compact, we have to have plastic classification. So you may see that plastic classification is even more stringent, meaning that each plate in a hot roll section, for example, has to be thicker. So B by T ratio is smaller in comparison to compact section. That means the plates have to be thicker. That is basically what it means, is that after, a plastic classification ensures that even after a very large rotation or very large strain, and that in cyclic conditions, the cross section does not undergo local buckling easily, and it can accommodate a lot of compressive and tensile plasticization over and over again. Now we will talk about some of the detailing aspects of rigid connections. So when we want a rigid connection to be ductile, we have to make sure that there are no risks of any fractures or premature fractures to happen in the connection. Wherever we have bolted connections, typically fractures can be controlled and we can avoid the modes in which a sudden fracture can happen. However, welds are relatively unpredictable in comparison to bolts, and the challenges are often lie in the workmanship, and some of the design provisions or some of the guidelines have been developed to avoid a premature failure or premature fracture of a weld. So there are various such considerations which avoid any defect or any kind of a inclusion in the weld which can trigger an early crack in a weld. We have to take all those precautions. In addition to that, you might see that, for example, in this situation, we may be required for us to be able to weld or groove weld this bottom flange to the column. We require a backing bar or a backing strip to be placed beneath the flange, so that this material can be deposited in that location. Now the interface between the backing bar and the column flange, which is only partially fused together, that interface becomes the point of stress concentration, and that's where the crack can start. And many such possible cracks have been documented in the literature and listed here. So this is a different type of a crack which is not starting from there, but this is starting only because of some problems with the hydrogen inclusion in the welding process. But in most of the other cases, you may see that the crack starts from that interface between the backing strip and the flange, bottom flange. So in all such situations, we have to be extra careful. Generally, the requirement is that we should back gauge, so we should remove this backing bar after the weld is done, and we should provide a smooth surface here. Also, the access hole which needs to be provided so that we can provide a weld, a continuous weld through the entire width of the flange. Sometimes we may introduce, the welder may introduce a defect or a sharp corner here that may give rise to the possibility of fracture in the bottom flange, and even that surface and even the geometry of this access hole is very strictly has to be adhered to, so that there are no sharp surfaces or no sharp corners in the entire geometry in order for us to be able to avoid such fractures. So with this slide, I am concluding this course. I was able to cover topics such as basics of welding and bolted connections, then the design of bolt groups and weld groups, then designing of frame members which are non-ductile detailed, and then some guiding principles for the design of ductile connections. Now, the handicap here is that in the Indian code, there are no detailed guidelines for the designing and detailing of ductile connections yet. One code is under development, so soon it will be published, and then we would have more strict and more uniform guidelines for such connections. Until then, we would have to follow some of the international standards or the basic principles, fundamental principles to design ductile connections or ductile frames. So I'm thankful for all the audience, for all the participants in the course. I look forward to offering this course again. This is where I will conclude. Thank you.